this episode, we're going to make kernel modules feel like a normal, understandable part of how Linux supports hardware and features, instead of something mystical that only experts touch. Many learners hear the word module and imagine it is an advanced customization topic, but at its core, a module is just a way for the Linux kernel to gain a capability without baking that capability permanently into the kernel itself. The exam includes this topic because modules sit at a crossroads between boot behavior, hardware detection, and system stability, and questions often use modules as the hidden reason why something works on one system and fails on another. You do not need to memorize obscure module names, and you do not need to learn a bunch of commands to do well. You need to understand what modules are conceptually, what triggers them to load, and what kinds of symptoms appear when the right module is missing or the wrong one is present. Once you can tell that story, module-related questions become predictable. By the end, you should be able to explain modules as drivers and kernel extensions, describe the typical load timing during boot and runtime, and use a calm reasoning process to connect symptoms to module issues. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Start by anchoring the idea that the kernel is the core of the operating system, responsible for managing hardware access, memory, and the rules of process execution. The kernel can be built in different ways, and one major design choice is whether a capability is built directly into the kernel image or packaged as a module that can be loaded when needed. A built-in capability is always present, like a fixed part of the kernel, while a module is like a plugin that can be inserted to add functionality. That plugin can be a hardware driver, a file system driver, or a feature component that supports a particular subsystem. The big advantage of modules is flexibility, because you can support lots of hardware and features without building one giant kernel that includes everything at all times. Modules also allow updates and changes in a more controlled way, because you can replace or adjust a module without rebuilding the entire kernel. For exam thinking, the key is to understand that modules are part of how Linux keeps itself adaptable across many platforms. This adaptability is why Linux can run on so many device types, and it is also why module management exists as a real concept. Kernel modules matter most when you think about hardware, because many hardware devices require a driver that knows how to communicate with them, and in Linux that driver often exists as a module. If the module is available and loaded, the device works. If the module is missing, incompatible, or not loaded, the device might not appear, might behave strangely, or might not function at all. For beginners, it helps to think of a module as a translator between the kernel and a device, because the kernel needs a way to send and receive the right signals. If you plug in a network card, for example, the kernel needs a driver to recognize it and operate it. The exam often tests this indirectly by describing symptoms like a device not being detected, a file system type not being recognized, or a feature that works on one machine but not another. In many of those cases, the module is the missing link. Your job is not to name the module. Your job is to recognize that the kernel needs an extension to support that capability. Now let's talk about when modules load, because timing is a huge part of how to reason about module-related issues. Modules can load during boot as the system detects hardware and prepares the environment, and they can also load later while the system is running in response to new devices or configuration changes. During boot, the kernel initializes core subsystems and detects hardware, and the system uses rules and discovery processes to decide what modules are needed. This is closely connected to the early boot environment you learned about earlier, because the system may rely on an early user space environment to load certain modules before the real root file system is fully available. This is especially important for storage drivers and file system drivers, because if the kernel cannot access the storage where the system lives, boot cannot continue. That means some modules must be available very early, while others can wait until later. For exam scenarios, if a system fails before reaching a usable environment and the symptom points to missing access to storage, a missing early module is a plausible explanation. If a system boots but a peripheral device is missing, a later module load issue becomes more plausible. Timing helps you separate boot-critical module issues from runtime module issues. A useful concept is automatic loading, because in many cases you do not manually load modules. The system loads them automatically based on detection and configuration. Automatic loading is like the system saying, "I see this hardware identifier, so I will load the driver that matches it." That implies two important things for exam reasoning. First, if the hardware is not detected properly, the module may never be loaded, even if the module exists on disk. Second, if the module exists but is not associated with the detected hardware, it may not be chosen automatically. This is why module issues can look like hardware issues, because the kernel cannot use a driver it does not know to load. It is also why a change in system configuration can cause a device to disappear, even though the device did not change. When you see this pattern, think about the chain of detection, matching, and loading. The exam may describe this as a device not appearing after an update, which can be consistent with a driver change or a mismatch between the kernel and the module. You are building a habit of looking for the invisible decision point where the system decides what to load. Another concept that makes module reasoning easier is dependencies between modules, because modules themselves can rely on other modules. A driver might require a core subsystem module, or a file system module might rely on a lower-level support module. This creates a hierarchy of loading, where one module can trigger or require others. In an ideal world, the system resolves these relationships automatically, but conflicts and mismatches can still happen. For exam-level understanding, you do not need to trace complex dependency graphs, but you should know that modules are not always isolated. If a device requires a chain of support, missing any link can break functionality. This is why module-related failures can sometimes look inconsistent, such as a device partially working but missing an advanced feature, because only part of the chain loaded successfully. Dependency thinking also helps you interpret why a single module name might not be the full story in troubleshooting. The safe approach is to think in terms of capability layers. The kernel needs a base subsystem, then a driver, then possibly additional support modules. That layered perspective aligns with how Linux is built. You also need a basic understanding of what a module file is and where it lives conceptually, without turning this into a path memorization exercise. Module files are typically stored as part of the system's kernel-related files, organized by kernel version so that modules match the kernel they are intended to work with. The reason version matching matters is that the kernel and its modules are designed to work together, and a mismatch can cause a module to fail to load or to behave unpredictably. This is similar to the idea you learned with initramfs pairing, where the kernel and early environment must align. On the exam, you might see a scenario where a kernel update happened and then hardware support changed, and that can be explained by module compatibility or availability. Another common pattern is that a system boots into a different kernel than expected, and the module set loaded is different, which changes device availability. You do not need to manipulate kernel versions to answer the question. You need to recognize that kernel version and module set are linked. Once you recognize that link, you can interpret symptoms that follow updates or boot selection changes more confidently. Now let's address a common misconception, which is that modules are only for optional devices and that core functionality is always built into the kernel. In reality, many core capabilities are modular, including some storage drivers, network drivers, and file system support, because modularity helps distributions support many configurations without shipping dozens of different kernels. That means modules can be critical to boot, not just to convenience. This is why the early boot environment sometimes includes modules needed to access the root file system, and why missing module support can cause a system to drop into an emergency environment. A beginner might assume that if the system is failing to find the root file system, the disk must be corrupt, but an equally plausible explanation is that the kernel does not have the driver it needs to access the disk or the file system type. The exam likes this because it tests whether you can think of driver support as part of the chain, not just file content on the disk. If you remember that core features can be modular, you will avoid overly dramatic conclusions and choose safer, more accurate explanations. This is the kind of reasoning the exam rewards. Security is another reason modules matter, because modules run in kernel space, which means they execute with very high privilege. A bug or malicious behavior in a module can have serious impact, because it is operating inside the most trusted part of the system. This does not mean modules are inherently dangerous, but it does mean module loading is often controlled and monitored in real environments. For exam purposes, you should understand that loading a module is not like running a normal program. It changes the kernel's capabilities directly. That is why systems may restrict who can load modules and why organizations care about which modules are present. This security angle also connects to stability, because a poorly matched or buggy module can crash or destabilize the system more severely than a user application might. In exam questions, you might see hints about stability issues after adding new hardware or after an update, and module behavior can be part of the explanation. The safe reasoning is to treat module changes as high-impact changes, especially compared to user-level tweaks. That mindset helps you choose cautious answers when multiple choices could solve a problem. Another useful way to reason about modules is to think about symptoms in terms of what layer is failing to provide a capability. If a device is completely absent, the driver module might not be loaded or not available. If the device appears but does not function correctly, the module might be loaded but misconfigured, incompatible, or missing a supporting module. If the system fails during boot while trying to access storage, a boot-critical module might be missing or not included in the early boot environment. If a feature works until a reboot and then disappears, you might suspect that the module loaded temporarily during runtime, but is not being loaded automatically at boot. These are not rigid rules, but they are powerful heuristics that help you interpret the small stories the exam provides. The key is that modules are often the difference between the kernel knowing how to interact with something and the kernel being blind to it. When you treat modules as capability providers, the symptoms become easier to map. This is the same kind of stage dependency reasoning you used in boot flow topics, now applied to driver and feature support. Finally, tie module thinking back to the bigger Linux plus exam skill of choosing the least risky interpretation that matches the evidence. If a scenario indicates hardware was added and then a device is not recognized, consider the module support chain before assuming the hardware is dead. If a scenario indicates a kernel update and then a feature changed, consider kernel and module version alignment before assuming the system is randomly broken. If a scenario indicates the system fails before reaching normal user space with a message that suggests it cannot access storage, consider whether the kernel has the right driver and file system support at that stage. These are all examples of using a structured story rather than guessing. The exam will often include distractors that point you toward user accounts, network configuration, or permissions even when the issue is fundamentally kernel capability. When you recognize module-related patterns, you can eliminate those distractors quickly because they do not match the layer where the failure occurs. That saves time and reduces stress, which is part of exam success. By the end of this lesson, you should be able to describe kernel modules as loadable pieces of kernel functionality, often drivers, that allow Linux to support a wide range of hardware and features without building everything permanently into the kernel image. You should also be able to explain when modules load, including early in boot for critical capabilities and later at runtime when new devices appear, and you should understand how automatic loading depends on detection and matching. You should recognize that modules can have dependencies, that kernel and module versions must align, and that module issues can present as missing devices, partial functionality, or boot failures that look like missing storage. Most importantly, you now have a reasoning approach. Place the symptom in the boot timeline, identify the capability that is missing, and consider whether the kernel has the right module support to provide that capability at that time. That approach turns module questions into logic exercises rather than memorization contests. If you keep this framework as you move into hardware discovery and system troubleshooting topics, you will find that many scenarios become easier to explain because you can see how Linux builds capability in layers and how those layers can fail in predictable ways.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.